This PowerPoint goes with your waves, light, and sound notes. Please turn to the back of your note pages and you can start taking your notes on sound. Sound is a form of energy produced by vibrations in matter. If you recall from the heat unit, we have 3 different phases of matter that we study: solids, liquids, and gases. So yes, sound can travel through a solid as well as a liquid, but we are meant to hear sounds traveling through gases, specifically air. What I'd like you to do at this point is to take your hand, put it over your throat, and I want you to start making some noise saying, "Hey, science is awesome," and I want you to feel the vibrations. In order for you to produce sounds, your voice box vibrates. Air then comes out of your mouth and goes out into the surrounding area, and your ears capture that sound, and it comes in, it vibrates your eardrum, then sends an electric signal to your brain, and you receive the sound. At the beginning of the unit, we've already talked about longitudinal and transverse waves. Sound is a longitudinal or compressional wave. If you take your hand, put it in front of your mouth, and you start saying the words pat, 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 you'll actually feel the compression every time you say the letter P. Now for the age-old question. If a tree falls in the forest and there's nobody there to hear it, does it make a sound? Well, if we go back and we look at our actual definition of sound, which is a vibration in matter, well, yeah, then the tree does make a sound. When it falls, it does vibrate. It vibrates through the solid ground, and it vibrates through the air. And if there's a lake nearby, I'm sure it will vibrate through the water. So just to recap, sound can travel through solids, liquids, and gases. You can put your head down on the table, tap your finger a little bit. You can hear the sound travel through the table. I'm sure you've been underwater, swimming at some point, and someone called your name or said something, and you kind of heard them underwater, and you looked up. We are actually made to hear in gases, so that's why things sound clearer and they sound better to us when we're just standing and talking to one another. So it's hard for us to imagine that sound can travel through a solid or a liquid, but it can, and it travels at different speeds. Sound needs matter to travel through. Sound cannot travel through empty space. But the speed of sound does increase with 3 different things. It increases with density. The more dense the object, the faster the sound moves. It increases with temperature, because as we know, when we add temperature to an object, the molecules inside start to move faster, thus increasing the speed of sound. And finally, elasticity, like a rubber band. If the molecules are stretchy, they can bounce back to their original spot very quickly. Therefore, sound can travel faster through something that is elastic. So here on this table, we see the speed of sound through different types of matter. The mediums being air, water, seawater, plastic, steel, aluminum, and the special kind of glass called Pyrex glass, which is very dense. So to try and understand the distances, think about the track that's outside. It's a 400-meter track. So if I were to make a sound, and by the time I said 1/1000, which is 1 second, that sound will have traveled through air almost the entire length around the track one time. So 343 meters is approximately equivalent to a turn, a straightaway, a turn, and then about halfway down the next straightaway. So you're almost 1 lap in 1 second. Now look down at the seawater, which is salt and water. So it's a little bit more dense, and sound can travel a little faster. So if you see, it's 1,500 meters. Well, 1,600 meters is a mile. So sound can almost travel 1 mile in that same second in the water. And that's because the salt adds a little bit of density there and makes the vibrations travel faster. Now look down at Pyrex glass. This is the most dense that's on the list, and now look how fast sound can travel. We're looking at 5,600 meters. So the speed of sound picks up a lot in that case. So here you see the 3 different types of matter: solid, liquid, and gas. Inside, the particles are packed really close together. They don't have to travel very far in order to vibrate and transfer the energy to the next particle. Whereas the liquid molecules have to move a little farther to transfer the energy, and then finally gas has to move the farthest in order to transfer its energy from one molecule to the next. So this is why you have these different speeds. The denser the object, the faster sound can travel because the molecules are closer together. The energy moves through quickly. As opposed to something that is less dense, where the molecules are farther apart, it takes longer for the individual molecule to transfer the energy from one to the next. So it may seem that sound travels pretty quickly. I mean, it gets almost a whole way around the track in 1 second. But light actually travels a lot faster, which we discussed earlier. So this is why when there's a thunder and lightning storm out, you see the lightning, and then you hear the thunder. They happen at the exact same time. Just the light travels so much faster, it gets to you quicker. Sound travels slower, it takes a little while. Also, when you go to watch fireworks, you see the firework, the light from the firework first, then you hear the bang that created the firework. So we measure sound with a variety of different types of units. So first we can talk about the pitch of the sound. That's how high or low the sound is. And I want you to imagine a piccolo in the band. It's a very high-pitched instrument. And then think of the tuba. It's a very low-pitched instrument. Usually size has everything to do with pitch. The smaller the object, the higher pitch the sound. The larger the object, the lower pitch of the sound. The other thing that we use is frequency. Frequency is the actual measurement of the number of waves that pass by in a second. That is used to determine frequency. The more waves that pass by in a second, the higher the pitch. The fewer waves that pass by in a second, the lower the pitch. We measure this in what is called hertz.
Another way that we're going to measure sound is what is called loudness, how loud or soft the sound is. And loudness itself is the perception of intensity. It's how we perceive the energy of the wave. So in this case, it's really up to the person who's hearing the sound to describe whether it's loud or soft. It's a matter of personal opinion. Growing up in my house, my music was never too loud. But apparently, according to my mom, it was way too loud. I used to get her banging on the door telling me to turn it down and that I should probably be studying more. All right, so the next thing here we have is intensity. This is the actual measurement that we make of the wave, and we measure it in a decibel. When we measure intensity, we're measuring the amplitude or height of the wave.
All right, so what we have here are pictures of an oscilloscope. The oscilloscope takes a longitudinal wave and turns it into a transverse wave that we can now take a look at and we can examine for our frequency, which gives us our pitch. We can also examine it for looking at how loud or soft the sound is. So let's look at this first wave. This first wave basically only has 3 waves in it. So here's 1, 2, 3. So this wave would have a frequency of 3 hertz. That's a pretty low-pitched sound. Now the one on the right, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8 waves, and then there's about a half of a wave left over. So this would be 8.5 hertz. So in this case, there are more waves per second. So this wave on the right has a higher pitch. Now, if I look at this again, I can also tell how loud or soft the sound is. If I have a very low amplitude, that's this measurement right here, then I have a very soft sound. If I have a very high amplitude, like in this wave over here, then I have a very loud sound. So we're going to look at 2 things. We're going to look at the frequency, which tells us the pitch. Then we're going to look at the height of the wave, which is going to tell us if it's loud or soft. So if you'd like to earn some extra credit, and if you're viewing this video on the Google Doc, what you can now do is follow the video along, and then you can look at the oscilloscope pictures below, and you can complete that for extra credit. Don't forget to press submit, so this way you get your full credit. Good luck.